Hello everyone, and thank you for watching my video today on the LaGrange error bound. All right, this is generally one of the more difficult topics in Calculus BC. I will do my best to walk us through it and what it means and how to do a couple problems. And hopefully you will walk away today knowing how to find the LaGrange, or some people call it LaGrange, error bound. The focus for this topic will be to investigate how close our Taylor approximations that we just talked about in our last section are to the actual value of the function's value. So let's first talk about the remainder of a Taylor polynomial. So this guy Taylor, who was a very smart man back in his day, decided that, well, we're going to do these Taylor approximations. They're not going to be perfect, right? But our original function would equal our approximate value plus some remainder that we're missing, okay? The remainder will serve as the error in our approximation. So essentially, our error would be the absolute value of this remainder, which we can think of as the actual function itself minus our Taylor approximation, which you can tell just by subtracting this over here is the same equation. Quick tip over here, we also often use the words remainder and error interchangeably in this section and in calculus. All right, so the general theorem here below gives us a procedure for estimating the remainder associated with a Taylor polynomial. The theorem, often called Taylor's theorem, defines a remainder that, when isolated, is referred to as the Lagrange form of the remainder, or the Lagrange error bound. All right, so here we have a Taylor polynomial of nth degree plus some remainder n at the end, okay? This remainder, the absolute value of it, can be given by the next term of the Taylor polynomial. So what we can go off of, here's what this Taylor guy discovered, is that is always going to be less than or equal to basically the next term. But the next term, what we're going to do is we're going to replace this with the maximum value of the n plus first derivative at some number z. This notation represents the largest value that this derivative will take on for some z value that will lie between our c value and our x value. Okay, so a couple quick keys before we start looking at a couple problems. One, we're not finding the actual error. We're bounding it. We're saying this is the biggest the error could be. Two, we're still using the first unused term, the next term in the Taylor series. Three, we often overestimate the error bound since we really can find the actual value of it. We overestimate the best we can. And four, we will find the value of that max in one of three ways. We'll give a graph. We can find a clear bound on that graph. If it's sine or cosine, it's great. The max is 1. Or we're told the max value. Now, it's not always going to be one of these three ways. But a fourth way usually be pretty obvious if we get there. So with that being said, let's take a look at our first problem. The third Maclaurin polynomial for sine x is given by p sub 3 of x equals x minus x cubed over 3 factorial. So great news, they already gave us the Maclaurin polynomial. Use Taylor's theorem to approximate sine of 0.1 by p sub 3 and determine the accuracy of the approximation. All right, so first of all, we're going to approximate sine of 0.1 using our Maclaurin approximation polynomial here, right? So that's going to be approximately 0.1 minus 0.1 to the third over 3 factorial. Go ahead and pull out your calculators if you want to. You're going to get a pretty small number here of 599 over 6,000 as a fraction, or 0.09983 repeating as a decimal. Okay, so that's the first half, determining our approximation. Now the accuracy. So we're going to use this right here as our accuracy. So we're going to do absolute value, r sub 3 of x, has to be less than or equal to the absolute value of the maximum value of the fourth derivative of some value z over 4 factorial times 0.1 minus 0 to the fourth power. All right, so now let's think about what these numbers can be as we put them in here. So the maximum of the fourth derivative, so this is a sine function, so the fourth derivative, the maximum, whatever that is going to be, it's going to be negative 1 or 1. So we're going to say it's 1 over 4 factorial of 1/10 to the fourth power. Still talking about the absolute value of that. All right, so that's 1 over 4 factorial, 4 times 3 times 2 is 24, times 1 over 10 to the fourth is 10, 100, 1,000, 10,000. So that's 1 over 240,000. So the accuracy of that error is less than or equal to 1 over 240,000. We're within 1 over 240,000 of the actual number when we use a third degree Maclaurin polynomial. If you want to find the actual error of this, now this is something you've probably learned before, but the actual error, remember, is just absolute value of the actual answer minus our approximation. So you can go ahead and find the actual answer via your calculator, sine of 0.1, and type that in. You'll see what the actual error is. And it's going to give me scientific notation here, 8.331 times 10 to the negative eighth, which is absolutely going to be less than this number. We're in good shape. Second thing we could be asked to do here is to find a range of possible values for an approximation. All right, so find the third degree polynomial approximation for e to the x at x equals 1, centered at 0. Use Taylor's inequality to find the range of possible values for e to the x at x equals 1, centered at 0. All right, so first of all, n equals 3. All right, center equals 0, x equals 1, and f of x equals e to the x. That's all the information that we know. All right, so if we use our third degree approximation, this is going to be another Maclaurin, because it's centered at 0, right? So first we have e to the 0, which is 1, plus the first derivative at 0, which is 1, over 1 factorial, which we want to write that, so I'm not going to bother writing that, times x minus 0 to the first, okay? Plus the second derivative at 0, which is still 1, over 2 factorial times x minus 0 to the second, plus the third derivative at e to the x at 0, which is still 1, over 3 factorial times x minus 0 to the third. So we're left with this. Okay, and if you want to simplify that, 1 plus x squared over 2 plus x cubed over 6. Okay. So we're still approximating that. So what we're going to do here is we're going to put our number in, our number 1 at x equals 1, right? So we're trying to find our P3 of x at 1. It's going to be 1 plus 1 plus 1/2 plus 1/6. And you can use your calculator to simplify that if you need to. It's going to give us 8/3. All right, so that's the first half of this question. The first half of the question is to find the third degree polynomial approximation for e to the x at 1. One thing I probably should have wrote here. This is P sub 3 of x there. Okay, so now we're going to use Taylor's inequality to find the range of possible values for e to the x at x is 1 centered at 0. So let's start by writing our error bound here. All right, so that's going to be absolute value, maximum of the fourth derivative of z over 4 factorial times, so again, it's x minus c, right? So 1 minus 0 to the fourth. All right, so the maximum value here, what are we going to put in for that? Well, let's think about the fourth derivative of e. The fourth derivative of e is e to the x. And if you were to put 1 in for that, you would get back what e would be, which is about 2.7. But we're going to overestimate this. We always overestimate, so we're going to say 3 is what we're going to be our max there. All right? So we're going to put 3 in for our max over 4 factorial, which is, again, 24, times 1 to the 4th, or just times 1. So this is going to be 3/24, or 1/8. So we need our remainder here. Our remainder is going to be, our error bound here is going to be less than or equal to 1/8. Okay, so now to get our range of values here for this, for E, let's say it's an under approximation or an over approximation, right? If we take our approximation and we subtract 1/8, E has to be greater than that. If we take our approximation and we add 1/8, E has to be less than that. Okay, so that would be, if we can use our calculator to get these, 2.5416 repeating is less than E, is less than 2.7916 repeating, is greater than E. And if you know what E is, remember E is approximately 2.71828, which is absolutely in that interval right there. Example 3, approximating a value to a desired accuracy. Determine the degree of the Taylor polynomial P sub n of x expanded about c equals 1. It should be used to approximate ln of 1.2 so that the error is less than 1/1000th. Okay, so we don't know n here. We do know c is equal to 1. We know our function is ln of x, all right? And we know our x is 1.2 as well. And we know our error bound is to be less than 1/1000th, okay? Okay, so if we wrote out our Taylor polynomial, all right, that's going to be f of c, which is 0, right? ln of 1 is 0, plus the first derivative, which is 1 over x, so 1 over 1, times x minus c, plus the second derivative. Now the second derivative would be negative 1 over x squared, so it's going to be minus 1 over 2 factorial times x minus 1 squared, plus the next derivative would be 1 over x cubed, so that would be 1 over 3 factorial x minus 2 cubed, plus so forth and so on. Okay? So if we're going to approximate natural log of 1.2, that's going to be approximately equal to our polynomial here. So we're going to put 1.2 in for x, and we get 0.2 minus 1/2 times 0.2 squared, plus 1/6 times 0.2 to the third, plus forever, right, until we know. All right, so let's first talk about now what would our nth degree derivative of 1 be. So the absolute value of the nth derivative of 1. Okay, so whatever this is going to be here, if we keep taking derivatives, all right, it's just going to be 1 over that, 1 over that, 1 over that. So it's going to be less than, it's going to be equal to, n minus 1 factorial. Okay, so now I have my absolute value of my remainder. That's going to be less than or equal to. All right, so my max function here, let's go ahead, max of f to the n plus 1 derivative of z all over n plus 1 factorial, 0.2 to the n plus 1. Right, and again, that's just the same formula that we've been using right here, right? Max and x minus c to the n plus 1 all over n plus 1 factorial. Okay, back to here now. So we said our max, if is this, right? If we put n plus 1 in there, we have n plus 1 minus 1. So that's just n factorial over n plus 1 factorial times 0.2 to the n plus 1. I'm running out of room here. Okay, so now n factorial over n plus 1 factorial, so this is 1 over n plus 1. And then we have 0.2 to the n plus 1. And if I rewrote that using some algebra, it'd be 1 over n plus 1 times 5 to the n plus 1. And we need that to be less than 1/1000. Which means, if we took the reciprocals of those, n plus 1 times 5 to the n plus 1 has to be greater than 1,000. All right, so at that point, we can kind of just play around with what that would, what we would need to do to get that. You could do a little bit more algebra if you wanted to. N plus 1 times 5 to the n times 5 is greater than 1,000. So n plus 1 times 5 to the n is greater than 200. Okay, and again, just really at this point, just kind of play around with what we get there, and you end up getting that n would be 3. Okay, we would need, in order for this statement to be true, it can't be 1, it can't be 2. But if n is 3, that statement would finally be true. All right. So you might be thinking, where did this come from? And I do want to explain that a little bit more. If we just kind of built our derivatives, right? We kind of built through our derivatives of this power, right? So the first derivative would be 1 over x. The second derivative would be negative 1 over x squared. The third derivative would be negative, so negative x and negative 2 would be positive 2 over x cubed. All right, the fourth derivative would be negative 6 over x to the fourth. And one more. How about one more? X to the fifth. So the fifth derivative would be positive 24 over x to the fifth. All right, you can see what's happening in the numerator. It's just n factorial. Well, it's actually n plus 1 factorial. Going on the numerator there. Sorry, n minus 1 factorial going on the numerator there. So like this would be 2 minus 1 factorial, 3 minus 1 factorial, 4 minus 1 factorial, 5 minus 1 factorial. So we're basically left with n minus 1 factorial is where that's coming from. And that's how we know this here. Okay? So we're just about done here. We're going to do one more problem. An old-fashioned AP example. So the function f has derivatives of all orders for all real values of x. Let p sub n of x represent the nth degree Taylor polynomial for f at x equals 1. Show that basically it's saying the error bound is less than 1/12. All right, so what do we know? We know that n equals 3. How do I know that? Right there. Okay, I know x equals 1/2. How do I know that? That's those numbers right there. And I know c equals 1. That's my center. Right there. So those are all things that I know right away. All right, so my remainder here is going to be less than or equal to. Now remember, we're doing the max. I'm just going to go ahead and show you that formula again here. The max of the n plus 1 derivative at some value z over n plus 1 factorial over x minus c to the n plus 1, right? So we have max of f to the n plus 1 derivative of z over n plus 1 factorial times x minus c to the n plus 1. All right? So we're just going to put the numbers in where they belong. I'll come back to the max here in a second, but n plus 1, since n is 3, that's just going to be 4 factorial. And then x minus c is 1/2 minus 1 to the 4. So the max, what's this max number here going to be? And I just realized that I forgot to put the graph on here of this. There's supposed to be a graph, which I will add on to the notes before we do this. There's supposed to be a graph of the fourth derivative. This is the fourth derivative, and it kind of looks something like this. This is 30. The max would be 30. Okay, so I apologize for not having that picture up here, but I will put it on the notes before we do these. So anyway, we get this here. All right, now we can simplify that down. So it's going to be 30 over 4 times 3 times 2, which is 24, times, and this is also supposed to be the absolute value there. So it's going to be 1/2 to the 4th. So that's going to be 5/4 times 1 over 16. So that would be 5 over 64. And for the final answer here, 5 over 64 is definitely less than 1/12. So we are good. All right, so I will go back and add this picture in that I missed before we take these notes here. But hopefully you got the picture. You kind of see what we did there. And that's it for today. So I hope you enjoyed our video. I hope you learned a little bit about LaGrange air bound. And we'll see you again soon.